Hey, today I'm going to talk about material optimization by combination of machine learning and analytical data for the development of photocatalytic materials. This is our recent progress of our machine learning study. So this one skip. So first, I'm going to talk about the problem of applying machine learning for materials, especially the inorganic materials. So as many of you know that in the machine learning uh, data, for example, chemical structure or parameters used as X and target physical properties Y is somehow correlated with Y equal f of X. And during the machine learning process, this functional form is constructed for further prediction of the new materials. For example, in the drug discovery process, you have various molecules which have uh, medical activity and why, and these two are correlated to find out new drug candidates. And this research has been mostly extended into the material informatics called MI. And in the MI, for example, chemical space, such as chemical composition, species, and structures. Simply, if you think about the chemical formula like this, and you can do the DFT calculations, or you can collect the necessary information from the database, and which are correlated with the target physical property or structure. Right. However, in many cases of the MI applications, the problem is the data number because it usually need more than 1,000 data is needed. So in the research trend, to increase the number of data, the robotic automation has been uh, developed to automatically increase the number of the data of the chemical synthesis. However, when we think about inorganic materials, there are several other problems in the machine learning. For example, in for the application of catalyst, the chemical structure is correlated with the selectivity of the reaction. And for example, this kind of molecules, you can define this kind of molecule with a ring number, molecular weight, or lone pair, because and in the computer calculation, molecular structure need to be converted to the numbers, which is called descriptors. And molecular case, it's not so difficult to define the molecule by the descriptors. On the other hand, in the case of inorganic materials, for example, here, as you know, the photocatalytic water splitting, and the light energy is converted to the water splitting reaction. And one of the famous materials is hematite, Fe2O3. And can you describe this as Fe2O3? But the performance itself is actually, in the case of inorganic materials, it depends on the other factors such as thickness, crystallinity, defect, and impurity. So you cannot just say this material as Fe2O3. At the same time, in the case of the molecule case, since you can easily convert it to some specific descriptors, that's why you can do the quantum calculation. Then you can increase the number of data over 1,000. However, for the same reasons, uh, as I mentioned, in the case of inorganic materials, still you need to prepare the different type of samples, and in the lab scale, the practical number of the sample differences maybe around 100. So what can we do using this kind of small data set when we apply it for machine learning? We think about that as we use the analytical data for the materials because analytical data as correspond to the specific materials you prepared. So, and it can be a good descriptors for the materials. So we have here we are going to show you our methodology to predict the performance by combination of machine learning and analytical chemistry. Here's a hematite again, and hematite can be prepared by the solution deposition method. And when you prepare the sample, usually the IV curve, which corresponds to the photocurrent value when applying the bias potential, the target performance of the photocurrent is varied with a kind of a large variation, right? So even under the same experimental condition, materials often have a large variation of performance. So in this case, you cannot apply the machine learning because you use the same condition and the same material. So meaning that X is same, but Y varied. You cannot predict different Y using the same X values, right? So in this case, you cannot use the machine learning. So that's why we introduced analytical data to represent each of the materials. So X is taken from the analytical data and they are tabulated. And then the performance Y is predicted using by the machine learning procedure, right? So here's again the hematite case, and we prepared various types of the hematite by modifying the calcination temperatures, and about 100 samples were prepared. And what we did use as prepared X is analytical data. So we measured UV vis, XRD, Raman, and photoelectrochemical impedance spectroscopy. And we took peak intensity and the position, all of the features in the analytical data. And in the case of PEIS, we took the several electrical parameters by fitting. And as Y value, which is the PEC curve, and we took the photocurrent at 1.23 volt and the water oxidation potential. And it varied like this. So during the machine learning scheme, X are the tabulated analytical data, and they distributed something like this. And some of the analytical data didn't have any variation. In this case, it doesn't help for predicting the Y value, so they are removed. And also in the analytical data, some of the analytical data had a similar tendency. In this case, machine learning cannot decide which one is supposed to be used. In this case, we grouped some of the categories, making a cluster. And then after arrangement of the table, we use it for prediction of Y value. And not all the analytical data are important. So we did the descriptor selection. In this case, we use a recursive feature selection, which suggests first pick up one of the analytical data to predict and then find out the best one. And then add another one. And then gradually the prediction accuracy going to be saturated. And then we selected the important features. After that, we can do the evaluation called the sharp analysis, which indicate how much important for each of the descriptor analytical data to predict the performance. Right? And finally, we can construct the functional model during this process. So y is predicted by x values, and 80% of the data is used for training, which means construction of the functional form of y equal f of x. And using rest of the 20% and known for this functional form, the prediction accuracy is tested by the test data. And this combination is randomly changed and then averaged, which is called cross-validation. Right? So when we apply this for hematite materials, this is the training result and the test result. This is actual photocurrent and predicted photocurrent. So meaning when the plots are on the y equal x, it gives a good accuracy, and accuracy is evaluated by the R2 value. Simply, if it's closer to 1, it's better. So when you use the experimental data, if the R2 is over 0.8, it's a quite good prediction, I suppose. And then we can do the sharp analysis, and then we can know each one of the parameters, how much important to predict the performance, and we can identify the important electrical parameters and then crystal facets. So this strategy works very good, even for a small data set, right? So what I want to tell you is this strategy actually works well because analytical methods has been selected over a long history of research in each field. That's why the resulting analytical data have potentially effective descriptors for materials. And then this strategy has been applied for various types of the materials and combinations. And then some of them are connected to the experimental condition to make the best performance of the material, right? Then move on to our recent study and then some of the examples. First one is the descriptor engineering to study the co-catalyst effect, right? So in water spreading, platinum ruthenium used for HER, and some oxide material used for oxygen evolution reaction, OER, and CO2 reaction, of course, some of the co-catalysts are used. So co-catalyst deposition is a general standard process for water splitting reaction, and it is believed that it helps surface oxidation and charge transfer. But how can you optimize it is still a trial and error. So in the photocatalyst, again, here the platinum for TL2 and a copper for hematite, and well-known some co-catalyst is believed to help the reaction efficiency. So here I will show you how to study the co-catalyst effect using this example. Here we use the copper on hematite, which is deposited by the photo deposition technique. And as X, we collected analytical data, PIS, Moshoki, FastScan CV, UV-Vis, and Raman spectrum. As Y, again, the target is a photocurrent value at 1.23 volt. And instead of we did the descriptor engineering to extract only the co-catalyst effect. Here the UV-Vis spectrum, right? With and without copy. So by adding the co-catalyst, absorption spectrum has been modified a bit. So we use descriptor engineering just simply by subtraction and normalize. So use the subtraction descriptors. Similarly, as a target value, by deposition of the copy, photocurrent increase. So we use the subtraction targets. Then we use the machine learning, and it actually works very nice for training and test data. Even for test data, R2 is over 0.8, which is very good prediction. And we could analyze by the sharp analysis. And one of the results I will explain here, this R3 is the solution interface resistance. And this is very much reasonable because hematite has two surface states, S1 and S2. And S2 is originally a bad surface state for good inducing a recombination. However, copy is believed to help the reactions here or by depositing the S2 state. So it's very much reasonable. So what I want to say is we often modify the samples, right? So, but we can evaluate the effect from the sharp analysis, right? So other recent progress is how to improve. So we developed the operational sharp analysis. We want to improve the materials, right? So I show the sharp amplitude, something like this. And this one is the dominant descriptors. And this value is a contribution to the target. This graph is actually coming from this kind of scatter plot. And this indicate each sample and each descriptor has a sharp value. And this bar graph is simply averaged the amplitude of each of the sample data. So what we can do in the sharp analysis is we can identify the important descriptors, and then they are analyzed by sharp. And if sharp value is positive, it means it helps the improving the performance. It's negative, it has an opposite effect. So, for example, one of the analytical data is red is large value and blue is small value. In this case, X1 increased, the performance is good, meaning that X1 and X25 is a positive correlation. On the other hand, X9 is a red to blue, so it has a negative correlation, right? I'll show you one of the example in the case of the strategy improvement of the interface of the FTO and hematite interface. Insertion of TiO2 under layer is good for supporting the conductivity at the back interface. Without using the TiO2 under layer, here are the sample data, but once TiO2 is inserted, you can recognize that kind of very much small inactive sample has totally disappeared by inserting the TiO2 under layer. And also the average photocurrent value is almost 3 times larger. And we developed operational sharply. What and how it works. So this is the original sharp contribution. And we plotted this with and by changing the color depending on the experimental operation. In this case, with and without TiO2 layer. So you can easily recognize that this part is totally different, red and blue, and red one contributed nicely for the performance. So it tells you TiO2 and the layer actually affects the density of state of hematite and promoting the electron transport. Okay? And this is another example for alcohol deposition, but I will skip this one here. And in any case, you want to modify the experimental operation. However, what does it affect the samples? And you can tell it from the operational shot plate analysis. So here's our strategy. We prepare the sample, performance analysis, collection of the analytical data, and collection of the descriptors. And during this correlation, we do the machine learning. And during this process, we can find the important factors for the performance. Okay? All right. Then the final topic is the PEC curve prediction from SEM image using the deep learning prediction. All right. So many of you know here the PEC performance. And what if you take only SEM image, you can predict the whole PEC curve. That's great, right? And it's actually possible if you we only need SEM image to know the PEC performance. This is what we did. As you know, the photocatalytic performance is evaluated by the PEC performance during light irradiation. Photocurrent is measured. This is a photocurrent voltage curve. And this current corresponding to the photocurrent during the water oxidation process at 1.23 volt. And in the previous research, I showed you the photocurrent at 1.23 volt was predicted by the combination of the analytical data. However, we have whole curve. Actually, this curve is final output of the light absorption over potential, conductivity, recombination, and so on. So the whole curve prediction is very nice to understand the physical process, right? So what we did is originally analytical data, taking the features and do the prediction. However, in this case, SEMA images are used and directly predict the whole curve points. To do so, we use a convolutional neural network, which is often used for the analysis of the image data. So what we did is using the bismuth vanadate photoanode combination SEI image and BEI image and a double layer image to predict the IV curve. So here's the SEM images we used, and SEI and BI and the different magnification images were collected. And we use a convolutional neural network. I don't explain in detail here, but it's a quite general image analysis data. And as I said, SEI-BEI or a combination of SEI-BEI is used. This is quite similar. This overlay strategy is quite similar as a color image. Color image is the overlay of red, green, and blue, right? And any of the images are actually formed by the numbers. And these numbers are calculated by the convolution and then averaging and activity distinction. Then several times these calculations are repeated, and finally it is converted to the number of about 15 numbers corresponding to the photocurrent values. And the evaluation of the curve correspondence is evaluated by R2 values. So we have the prediction values and then experimental data. And when the R2 is near 1, it's predictable. So we decided the threshold value over 0.95 case, it's predicted. So what it means is R2 over 0.95 case is 31% in this case, in this example. So here, the example, first using the SEI images. You can see the R2 over 0.95 is about 50, 55, 51, and 41% for different magnification. So 4K or 10K magnification seems to have a good prediction accuracy. When changed it to BI images, it's actually jumped up to 2K case 67%, 4K 74, 10K 74, 50K 53%. And BI provides higher prediction accuracy. And again, the 4K and then 10K is better. And the effect of over the year, 4K and 10K is about 74%. By overlay of the images, this one almost the same, but in the case of 10K, it's almost about 80% now. And also the cut size of the image is also optimized. And this is using the Bayesian optimization. By changing the cut size of the images, the prediction accuracy was optimized. And in the case of 4K, this size is good. And in the 10K, this size was good. And actually, by using the optimized size of the images, in the case of 4K, R2 over 0.95 is almost 99%. In the case of 10K, 96%. So we can say that's almost perfect prediction of PC curves only from SEM images, right? And this is strategy works not only bismuth vanadate. We tested for hematite, and this one also 99%. So this strategy should work for various materials too. And finally, we analyze why this can help in understanding the PC card. This is the original SEM image, and we want to do the particle analysis. So we did the segmentation and took the statistical information of the particle intensity, area, circularity, solidity, oil number, and so on. This is the general features. And then using these X features, target of the photocurrent value was predicted, and the R2 value was actually quite high, over 0.94, around 94. Then we did a sharp analysis and clearly showed that the first, these three, blue is coming here. So these values are smaller the better. And the third one, this one is larger the better for the PC performance. What we can learn from here is like this. So the first one, in each of the particle, circularity, solidity smaller the better, meaning that and then Euler number is smaller the better, meaning that the complicated one is bad and simple size is good. And this one is elongated one is good. So this indicates simple oblique shape is good. And then the interparticle intensity, if the particle reflection secondary electron intensity is different, is good. So mixture of inhomogeneous particles is good. And for each particle, some distribution is good. So possibly gradient of conductivity would be good for the performance, right? So with that, so I talked about these topics, and so here's a general conclusion of this. So thank you very much for your kind attention.